In this recording, I will talk about the existence and uniqueness theorem for first-order ordinary differential equations. When solving equations, and I mean all sorts of equations, not just differential equations, it is useful to be able to tell, before trying to solve the equation, whether the equation actually has solutions and how many. For example, if we attempt to solve an equation that actually has no solutions at all, we could spare ourselves a lot of time and effort if we can somehow tell that the equation actually has no solutions before attempting to solve the equation. If we're working on another equation that actually has solutions and we found one or two, should we continue looking for other solutions that there might be? The existence and uniqueness theorem answers these questions. Namely, it states that under certain conditions, the initial value problems for first-order ordinary differential equations have a unique solution. Let me first explain why the theorem talks about the initial value problems rather than about differential equations themselves. You may have already seen that the differential equations typically have infinitely many solutions. For example, if we look at the simple differential equation y prime equals to 2x, we find that it has infinitely many solutions. In fact, its general solution, which is easy to find by integrating the right-hand side, is y equals to x squared plus c, where c is an arbitrary constant. On the right-hand side of the screen, you see the graph of the solution curves. These curves are parabolas, and we observe that no two such parabolas ever meet or touch each other, and the plane is being filled up by these parabolas. Through every point of the plane, there passes a unique parabola, which is a solution of this differential equation, a graph of the solution. Now, if we impose an initial condition, for example, if we're requiring that our solution have a specified value at x equals to 0. For example, suppose we're looking for the solution whose value at x equals to 0 is 5, then it is easy to find that the value of the constant c in this case must be 5. Just plug in x equals to 0 and y equals to 0, y equals to 5 in the general solution to find that the constant c must be 5. And so the initial value problem, the differential equation, together with the initial condition, has a unique solution, y equals to x squared plus 5. Now, at this point, you might be thinking, well, that's probably the case for any initial value problem. If you start with the first-order ordinary differential equation, you find the general solution, which is a one-parameter family of curves or formulas that contain one arbitrary constant c. Then you plug in the initial condition that allows you to determine the value of the constant c, which will be unique, and here you go, you'll find a unique solution. This turns out not to be the case all the time. And on the next slide, we will see an example of this. So here we're looking at two differential equations, which at first look quite similar. The first equation is y prime equals to negative 2 times square root of y. Second equation, y prime equals to negative y squared. Of course, the right-hand sides of these equations are different functions of y, but there is nothing that could suggest to us at this point that the behavior of the solution for these two differential equations is quite different. Before we look at the solutions of these differential equations in more detail, let's make first a few observations about the solutions that are easy to make. First, our differential equation on the left-hand side, y prime equals to negative 2 square root of y, is only defined for positive values of y or y equals to 0. It's not defined for negative values of y. That is because y is under the square root. And so the solution curves will be located in the upper half plane of the coordinate plane. The second differential equation is defined everywhere. The solution curves will again fill up the entire coordinate plane. Another easy observation is that the constant function y equals to 0 is a solution of both of them. So therefore, the x-axis is one of the solution curves for both of these equations. What we will see in a minute that the solution curves for the first differential equations, which are different from the x-axis itself, are curves that consist of a segment of a parabola and then a segment of the x-axis. Let me trace out one of these solution curves on the graph for you. So let's say we're looking at this point right here, and we're looking for the solution curve that goes through that point. In this upper portion of the solution curve, it's a parabola. So here's my red point moves along the solution curves. We're moving along the parabola until we get to the x-axis, and since that position, after that point, the parabola, the solution curve, the point is going to follow the x-axis. So that would be one solution curve. Now, if you start elsewhere, like for example here, again, you're going to slide down the parabola until the point gets to the x-axis, and then after that, the point will move along the x-axis. These are the solution curves for the first differential equation. Now, the solution curves for the second differential equation, one is, as I mentioned earlier, the x-axis, and the other solution curves are hyperbolas. And so what is quite different in these two pictures? Well, in the picture on the left, what we see is that any two solution curves actually intersect. Even more so, we can be even more precise. We can say that any two solution curves have infinitely many points in common because they share a portion of the x-axis between them. On the right-hand side, the solution curves never meet. If you look at the two different solution curves, they will not meet at a point. They do not intersect. Another simple observation that we can make about these equations without solving them is to note that the values of the right-hand sides of these equations cannot be positive. Therefore, the derivative of the solutions cannot be positive. And therefore, the solution curves can only slope downward or be horizontal. They cannot be sloping upwards. The major difference between the solution curves, the behavior of the solution curves for these two equations that I would like to draw your attention to is that all solution curves for the first equation intersect the x-axis and each other. The solution curves for the second equation never meet. Let's now find all solutions of these differential equations and confirm that the solution curves are the curves shown in these pictures. Let's begin with the first differential equation on the left. We already know that the constant function y equals to 0 is a solution of this differential equation. If this equation has other solutions, namely solutions that take a non-zero value at some point, we will be able to find them by separating the variables. In order to separate the variables, we need to divide both sides of this equation by 2 square root of y, which is possible if y is not equal to 0, and also by multiplying both sides by dx. We obtain dy over 2 square root of y equals negative dx. Integrating both sides, we find square root of y on the left hand side is the antiderivative of 1 over 2 square root of y. The integral on the right hand side equals to negative x plus c. At this point, we can solve for y by raising both sides of this equation to the second power to find that y equals to c minus x squared. Now, if we graph this function, we'll get a parabola which touches the x-axis at the point x equals to c. So the graph of this function will look something like this. Touches the x-axis at the point x equals to c. But here's an interesting question. So remember that we observed earlier, before we even started looking for the solutions, that the solution curves cannot go upward. And there's a segment of this parabola that is going upward. So there's something fishy going on here. It turns out that not all of this parabola is the solution curve. Only the left-hand side portion of it, from point C to the left of the point C, 0 on the x-axis, is the solution curve. The second part to the right of that point is not part of the solution curve. And in fact, I have to really erase this part. Why is that? Well, if we go back to this equation here, square root of y equals to negative x plus c, note that square root of y on the left-hand side cannot take negative values. Therefore, the values of the right-hand side also cannot be negative. And so we find that negative x plus c has to be greater or equal than 0. Solving this inequality for x, we find that x has to be less or equal than c. Now, does it mean that our solution is defined only for the values of x less or equal than c? It certainly seems to be the case. However, we also know that the constant function y equals to 0 is a solution, and these two solutions touch at the point c0. So what if we combine the portion of the parabola that we just drew, the left-hand side portion of the parabola, and the portion of the x-axis to the right of the point c0 to form another solution that is defined on the entire number line. In other words, what if we consider the following function, piecewise defined function, y equals c minus x squared for the values of x that are less or equal than c, and y equals to 0 if x is greater than c. This function, it's easy to verify, satisfies our differential equation. It satisfies that differential equation to the left for the values of x less than c, because that is the solution that we obtained by separating the variables. For the values of x greater than c, the solution is a constant function equal to 0, and we know that that is a solution of our differential equation. The only point where you might have some doubts about is x equals to c, but at that point the left-hand side derivative of the function is equal to 0, and the right-hand side the derivative of this function is also equal to 0. Therefore, the function is actually differentiable at x equals to c, and the derivative of this function at x equals to c is 0, which it should be for that function to be a solution of our differential equation. And so, in addition to the x-axis, our solution curves for this differential equations are curves that are part parabolas and part x-axis. Here is one of these solution curves corresponding to the value of c equal to 0.7. To the left of 0.7, the curve is a parabola. To the right of 0.7, the curve is a straight horizontal line. To help you see the solution curve better, let me show you the black point sliding down this curve and tracing it out. Note that the solution curve passes through the point 1, 0, 1.50, 2, 0, and any other point on the x-axis that is located to the right of 0.7. And so, in particular, this solution curve is the solution of the initial value problem, our differential equation, together with the initial condition y at x equals to 1 equals to 0. Now, if we change the value of c, we're going to change our solution curve. I'm going to decrease the value of c now, and this results in the parabola portion of the curve moving to the left. Now, by changing the value of c, we get a different solution curve, but note that this solution curve still goes through the point 1, 0. And so it still is a solution to the initial value problem, our differential equation taken together with the initial condition y at x equals to 1 equals to 0. Thus, we observe that the initial value problem, y prime equals negative 2 square root of y, the value of y at x equals to 1 equals to 0, has infinitely many solutions. And similarly, the initial value problems corresponding to the initial conditions given by a point on the x-axis will also have infinitely many solutions. On the other hand, it's easy to check, and please do so, the initial value problem corresponding to the initial condition given by a point not on the x-axis will have a unique solution. Now let's look at the other differential equation. Again, this differential equation is separable. It's fairly easy to separate the variables by dividing by y squared and multiplying by dx. The division by y is possible when y is not equal to 0. Next, we can integrate both sides. The integral on the left-hand side will equal to negative 1 over y. The integral on the right-hand side is negative x plus a constant c. And we can easily solve this equation for y to obtain y equals to 1 over x minus c. Now, if you graph these functions, you will see that the graphs of these functions are hyperbolas, which never touch the x-axis. And so, if you have a solution of this differential equation which takes a non-zero value at some point, it will never take the value 0. The solution curve that passes through a point not on the x-axis will never get to the x-axis. And therefore, the initial value problem y prime equals to negative y squared, y at x equals to 1 equals to 0 has a unique solution. Namely, y equals to 0. The constant function equals to 0 everywhere. Similarly, the initial value problem for this differential equation with the initial condition given by any other point on the x-axis will also have a unique solution, namely y equals to 0. Now, if you choose a point which is not on the x-axis for your initial condition, then the corresponding initial value problem will have a unique solution given by one of these equations, y equals to 1 over x minus c, and the corresponding solution curve will be a hyperbola. To summarize, the initial value problem y prime equals negative 2 square root of y, together with the initial condition, the value of y at x equals to 1 equals to 0, has infinitely many solutions, while a similar looking initial value problem, y prime equals negative y squared, together with the same initial condition, has a unique solution. We made these determinations by finding all solutions of these equations, and it took us quite a while to arrive at these conclusions. The existence and uniqueness theorem allows us to arrive at least some of these conclusions without having to solve the equations. Here's a general statement of the existence and uniqueness theorem for first-order ordinary differential equations. Suppose we are trying to solve the initial value problem, y prime equals to f of xy, where f of xy is some function or an expression in terms of x and y, together with the initial condition, the value of y at x equals to a must equal to b, then if the function f of xy and its partial derivative with respect to y are both continuous functions in a neighborhood of the point AB, and I remind you that the point AB is the point that gives us our initial condition in this problem, then this initial value problem has a unique solution on some neighborhood of the point x equals to a. Let's see how we can use the theorem to conclude that the second initial value problem has a unique solution. In this case, for the differential equation y prime equal negative y squared, the function f of xy is negative y squared. Its partial derivative with respect to y equals to negative 2y. Both of these functions are defined and continuous everywhere on the entire xy plane. Therefore, the existence and uniqueness theorem guarantees that the initial value problem y prime equals negative y squared, the value of y at x equals to a equals to b, has a unique solution regardless of what the values of a and b are. By contrast, if we look at the first initial value problem, in the differential equation y prime equals negative 2 square root of y, the function f of xy in this case is negative 2 square root of y. Its partial derivative with respect to y is negative 1 over square root of y. And we see that the function f of xy is defined and continuous for values of y that are greater or equal than 0. However, the partial derivative of f with respect to y, it is still continuous everywhere where it's defined. In other words, for positive values of y. However, it cannot be continuous for the value of y equal to 0, because if y equals to 0, then that partial derivative is not even defined. What does it tell us about the initial value problems that we are considering? So if we are solving the initial value problem, y prime equals to negative 2 square root of y, and the initial condition is such that the corresponding point AB is not on the x-axis. In other words, if b is greater than 0, then the existence and uniqueness theorem is applicable, and it guarantees that this initial value problem will have a unique solution. Now, on the other hand, if we're looking at the initial value problem, y prime equals negative 2 square root of y, and let's say the initial condition, the value of y at x equals to 1 equals to 0, in this case, the existence and uniqueness theorem is not applicable. Why is it not applicable? Well, because at this point, 1, 0, the partial derivative of f with respect to y is not defined, and therefore it is not continuous. Now note that the fact that the existence and uniqueness theorem is not applicable means simply that we cannot make any conclusion. We cannot make a conclusion that this initial value problem has infinitely many solutions. We cannot make a conclusion that it has a unique solution. We simply don't know. And one really needs to investigate further, for example, by solving the equation and trying to find particular solutions that satisfy that initial condition to find out whether or not this initial value problem has unique solution or not. In fact, we observed that this initial value problem has infinitely many solutions. Now I would like to explain why these two seemingly similar initial value problems behave differently in regards to the number of their solutions. Why do we get infinitely many solutions in one case and have a unique solution in the other? Of course, the existence and uniqueness theorem tells us that it has something to do with the partial derivative of the right-hand side with respect to y. It is continuous in one case and it is discontinuous in another case. But why does that condition on the partial derivative with respect to y enter in the statement of the existence and uniqueness theorem? Why is this important? Let me first remark that both of these equations that we've considered in this example are autonomous differential equations. An autonomous differential equation is an equation of the form dy dx equals f of y. In general, for a first-order differential equation that can be solved for dy dx, the right-hand side may depend on both x and y variables. We say that the differential equation is autonomous when the right-hand side does not depend on the independent variable x. And so an autonomous differential equation can be written in the form dy dx equals f of y, such as the two equations that we just considered. Next, I'm going to change the variable x to the variable t. It's not going to be a change of any substance. I'm just going to change the letter x to the letter t. And the reason I would like to do that is because I would like to interpret these differential equations as describing the movement of a point or an object along the y-axis. And I would like to think of the independent variable as being time. So we will use t to denote time. And so then we can write our differential equation in the form dy dt equals to f of y. We will have an initial condition, for example, y at 0 equals to b, and we can think of the differential equation as describing the movement of a point along the y-axis. dy dt is the velocity of the point, and what the differential equation says is that the velocity of the point is completely determined by its position at a specific moment of time, at any moment of time. So here are our differential equations written with x replaced by t, and we are going to think about two initial value problems, dy dt equals to negative 2 square root of y, the value of y at 0 equals to 1, and dy dt equals negative y squared, the value of y at t equals to 0 is equal to 1. We will find that we actually already know from what I've explained earlier that both of these initial value problems have a unique solution. However, there is a substantial difference that we will note here, and that difference is the difference that makes some other initial value problems for the first equation have infinitely many solutions, while for the second equation the initial value problem will always have a unique solution regardless of the initial conditions. So if we start with the initial condition y at t equals to 0 equals to 1, we're thinking of our point starting position with the starting position at y equals to 1. And note that the solution y equals to 0, the constant solution, is a solution of both of these equations, and therefore if our point at a certain moment of time finds itself at y equal to 0, then it will remain there indefinitely, forever. That is because the velocity of the object at y equals to 0 is 0. We will call such position an equilibrium position. An equilibrium position is a position where an object or point or a system, more generally, can remain indefinitely. And what I would like to do is I would like to see if we can calculate the amount of time the point will take to travel from y equals to 1, our starting position, to the equilibrium position y equals to 0. Let a be that time. So suppose a is the amount of time that it will take for the point to travel from y equal to 1 to y equals to 0. Then our solution will also satisfy the condition y at t equals to a equals to 0. And now we will determine what that a is. So let's remember that our differential equation is separable, so let's go ahead and separate the variables. And once we do, we will see that the y terms are on the left-hand side of our equation. But remember that y is actually a function of t, so we can think of the left-hand side is also being written as in terms of t, although we don't really know how y depends on t explicitly. But still, let's think of the left-hand side as being written in terms of t, and let's integrate both sides from t equals to 0 to t equals to a. And so what we will get is integral from 0 to a dy of t divided by 2 square root of y of t. And maybe let me emphasize that we're integrating over t, so I'll put our limits of integration as being from t equals to 0 to t equals to a. This integral will equal to the integral from 0 to a negative dt. Right? Now, the integral on the right-hand side is very easy to calculate. The antiderivative of negative 1 is negative t. We plug in the limits of integration, 0 and a, and we find that the integral on the right-hand side equals to negative a. What about the integral on the left-hand side? Well, if you remember the substitution rule for integrals, you will realize that the integral on the left-hand side is particularly well suited for making a substitution. Actually, the substitution is already sort of has been made there, because everything is written on the left-hand side in terms of y. I actually inserted that dependence on t specifically to be able to integrate over t. But now, let's change our variable of integration for the left-hand side from t to y. Under the integral, it's already, everything's prepared. I don't really need to do anything except remove that dependence on y. But we will have to change the limits of integration because now our variable of integration is y, and when t equals to 0, y equals to 1, so the lower limit of integration will be y. I can emphasize this by writing y equals to 1. And when t equals to a, y equals to 0, right? Remember that a is the time it takes the object or the point to travel to the equilibrium position, y equals to 0. And so what we find is that this integral on the left-hand side equals to negative a. And now we can solve for a to find that a equals negative integral from y equals to 1 to y equals to 0 of dy over 2 square root of y. Okay, so next, note that the negative sign in front of the integral can be absorbed into the integral. We can simply switch the limits of integration and remove the negative sign. And so I can write that a equals integral from 0 to 1 dy over 2 times square root of y. And now it's very easy to calculate this integral. The antiderivative of 1 over 2 square root of y is just y. And we can plug in the limits of integration into this antiderivative and then take the difference. Square root of 1 minus square root of 0, that is equal to 1. Okay, so what does this tell us? It tells us that if our point moves along the y-axis in such a way that its velocity at the point y equals negative 2 square root of y, then it will take 1 unit of time for that object to travel from y equals to 1 to y equals to 0. Once it arrives at the equilibrium position, y equals to 0, then the object will remain there indefinitely. We found one solution of the initial value problem that we started with. Now, however, if we look at a different initial value problem for this same equation, we will see that it can have infinitely many solutions. So for instance, let's now look at the following initial value problem. The equation is going to be exact same, y prime equals negative 2 square root of y. But this time I will say that our initial condition will be the value of y at t equals to 5 is 0. Now, this initial value problem will have many solutions. In fact, infinitely many solutions. Why is that? Well, first, what does our equation together with this initial condition says? It says that our point moves according to our differential equation, and that at the moment of time t equals to 5, the point is at the equilibrium. So one way in which this could have occurred is that our point has been at the equilibrium position indefinitely from the start, and it didn't move at all. That is our constant solution, y of t equals to 0 for all t. So that's one possibility. There's also other possibilities. We could, our point, our object could be starting at y equals to 1, right? So we can look at the solution that we've suppose y at 0 equals to 1. Well, then we know that y at 1 equals to 0, right? It takes 1 unit of time for the point to travel to the origin and to the equilibrium position, and then our point will remain at that equilibrium position indefinitely. In particular, at the moment of time 5, it will still be at the origin. So the solution obtained this way, by assuming that the point starts at y equals to 1, will also satisfy that initial condition that y at t equals to 5 equals to 0. So here you already see that the initial value problem has more solutions than just one, not unique solution. And if you analyze why this is really happening, you will see that essentially what makes this possible is that if the point starts at a position that is not an equilibrium position, such as y equals to 1, it then travels according to our differential equation, and it arrives to the equilibrium position eventually in finite time. And then it will stay there forever. Now, that is not the case for the second differential equation. Let's go ahead and look at that differential equation. So now we're looking at y prime equals negative y squared. Suppose our object starts at y equals to 1. The initial position is y equals to 1. And we would like to find the amount of time it will take for this object to arrive at the equilibrium position. So suppose a is that amount of time, then we are looking for a solution such that y at 0 equals to 1 and y at t equals to a equals to 0. We will follow exact same process as earlier to try to determine what that travel time a is. Separate the variables, dy over y squared equals negative dt. Now think of the left-hand side. Despite the fact that everything on the left-hand side is expressed in terms of y, but think of y as a function of t. And if you do, then you can integrate the left-hand side over t from t equals to 0 to t equals to a. On the right-hand side, we'll have exact same integration from t equals to 0 to t equals to a of negative dt. And just like earlier, the integral on the right-hand side is negative a. Solving for a, we again find that, and changing the integration on the left-hand side to an integration over y, we again find that a, the travel time from y equals to 1 to y equals to 0, will be the integral from 0 to 1 of dy over y squared. Now, what is this integral? What is the value of this integral? Well, let's go ahead and try to determine that. The antiderivative of 1 over y squared equals 1 over y. And to find the integral, we can now try to plug in the limits of integration, 0 and 1. Now, when we plug in y equals to 1, we get negative 1 over 1, and from that we need to subtract negative 1 over 0 this time. Now, this is, of course, undefined. We cannot divide by 0. Actually, if you think about this, the fact that we're getting here division by 0 is not particularly surprising. The function itself that we're integrating, 1 over y squared, this function is not defined at the endpoint of the interval of integration y equals to 0. If you try to plug in y equals to 0 into the function, you see that the function is undefined. So this integral is actually an improper integral. These are first signs that there is something interesting going on here. We're not able to determine the amount of time it's going to take for the object to arrive at the equilibrium position. Okay, well, since 0 seems to be a little bit of a problem, what if we try to calculate the amount of time it's going to travel it's going to take the object to travel from y equals to 1 to some point that is close to 0. So let's take a position such as epsilon, and the epsilon is going to be a small number that is close to 0, and we'll be trying to determine the amount of time it's going to take for the object to travel from y equals to 1 to y equals to epsilon. Well, that amount of time will again be given by a similar integral. It's going to be integral from epsilon to 1 dy over y squared. This integral is proper. The function of integration that we're integrating is defined and continues on the entire interval of integration, so there is no problem here. We can find the antiderivative, which is negative 1 over y, and plug in the limits of integration epsilon and 1. And what we end up with is 1 over epsilon minus 1. This calculation shows that for any epsilon that is not 0, if epsilon is not equal to 0, our object will arrive at the point y equals to epsilon in finite time, and this time equals 1 over epsilon minus 1. Let me write this down. So travel time from y equals to 1 to y equals to epsilon equals 1 over epsilon minus 1. So our object will get to the equilibrium position arbitrarily close. It can get arbitrarily close to the equilibrium position. However, will it ever arrive at the equilibrium position? Well, what happens when we let a epsilon go to 0? When we make epsilon smaller and smaller in order to determine how long it will take for our object to arrive at y equals to 0, what happens with the travel time? So when we let epsilon go to 0, the limit 1 over epsilon minus 1 doesn't exist, but more precisely you can say that that is an infinite limit. As values of a epsilon get closer and closer to 0, the values of 1 over epsilon are going to get larger and larger and larger, and they will get arbitrarily large. So the conclusion is that the amount of time it will take our object to reach the equilibrium position is infinite. In other words, our object will never reach the equilibrium position. Our object will never arrive at the equilibrium position at y equals to 0. Now, as a result of this, the type of phenomenon that we saw with the previous equation, where we saw that the initial value problem y prime equals negative 2 square root of y, with the initial condition y at 5 equals to 0, Remember, we found at least two different solutions of this initial value problem. One, the constant solution, where the point always is located at the origin, at the equilibrium position, it doesn't move. But we also had a second solution where our point could start at y equals to 1, and then it's going to travel and it's going to arrive at the equilibrium position in finite time, actually in unit time, and then it will remain there forever. And in particular, we will have a solution satisfying this initial condition that the value of y at t equals to 5 is 0. And so the fact that for this differential equation, the travel time to the equilibrium position is finite allows for several solutions to the initial value problem right here. But that is no longer the case. That is no longer the case for the second differential equation, y prime equals to negative y squared. Suppose we look at exact same initial condition for this second differential equation. Well, this time, the only solution for this initial value problem is the constant solution. Constant solution, y equals to 0 for all t. Why is that? Well, if we know that our object has to be at the equilibrium position at the moment of time t equals to 5, then it has to be there to begin with. Because if our object starts at any other position, not equilibrium position, then as we saw, it takes that object infinite amount of time to travel to the equilibrium position. Actually, we know the object will never reach the equilibrium position, and so it cannot satisfy this initial condition y at t equals to 5 equals to 0. And so the constant solution is the only solution to our initial value problem. To summarize, we observe that the fact that one of these initial value problems has a unique solution, while a similar looking initial value problem has infinitely many solutions, has to do with whether or not the travel time from a position that is not an equilibrium position to the equilibrium position is finite or infinite. Here is a graph of the absolute value of the velocity of the object versus its position y for both of these equations. If the absolute value of the object is equal to y squared, then we see that the velocity decreases gradually as we approach the equilibrium position y equals to 0. The point travels relatively slow compared to the other case, and the rate at which the velocity decreases when we approach the equilibrium position is slow. In the other case, the point travels a lot faster. The graph of 2 times square root of y is above the graph of the parabola y squared. But the velocity has to go to 0 at the equilibrium position, and since the values of the velocity are high in positions that are close to the equilibrium position, in order for this to be possible, the rate at which the velocity decreases has to be really large. In fact, if you think about the tangent line to the graph of 2 times square root of y at the origin, this tangent line is vertical, which means that the derivative of 2 square root of y with respect to y at y equals to 0 is infinite. And so we see that that partial derivative of the right-hand side of our differential equation with respect to position, which in this case is denoted by y, has to do with how quickly or how slowly the velocity decreases to zero when the point approaches the equilibrium position. If that decrease is happening very fast, it is possible for the point to travel fast as it approaches the equilibrium position, and that would make possible for that point to reach the equilibrium position in finite time. And that results in several, infinitely many, in fact, in our examples, solutions to the corresponding initial value problem. When a point travels slowly with a gradual decrease of the velocity as the point approaches the equilibrium position, the point doesn't travel fast enough to reach the equilibrium position in finite time, and therefore the corresponding initial value problem has a unique solution.